Okay, so hello. I'm Stéphane Bonnet. I'm the design authority of a modeling workbench for architectural design. So the modeling workbench is Capella. And I'm also a coach for model-based systems engineering, and I work for Thales Corporate Engineering.
Hello everybody, I'm Daniel Xertier. I also work at Thales Corporate Engineering. Thales Corporate Engineering is this transversal function inside Thales that helps our engineering team to be competitive in their engineering activities. So by helping them, this means that providing means to help them to do so. The means include tools, methods, support, consulting, know-how capitalization and reuse, and so on. So in terms of tools, Thales Corporate Engineering provides system and software and hardware engineering tools. And inside this activity, I'm in charge of the model-driven engineering domain. So this includes Capella. We will talk about Capella during this talk. Kit Alpha, it will be seen at the talk just after, and a set of other solutions. And I'm also in charge of the R&D part of this activity. So when we think about Capella, in fact, we think it covers system engineering. It provides means to perform system engineering. In fact, it's not system engineering, it's more architectural design. System engineering is more wider because it covers all the engineering means to define a system from the early phases of the development, from requirement, design, implementation, integration, verification, validation, qualification, during its operational usage until it's decommissioned. So, and it involves all the engineering disciplines for doing so. Architectural design is just the part that will define the architecture of the system itself. So as you see here, it's the conceptual model that defines the structural and behavioral part of the system. So all the components, the components of the system that interact between each other for performing the missions that are defined for the system, and different views of the system, because it's not only the structure and the behavior, but it's also constrained by a lot of different non-functional constraints, for example, performance, safety, and so on. And all the views together will end in defining the best possible architecture for the system. And Capella doesn't come on its own. Capella comes with a method, because the method defines how a system must be architectured, and Capella tools up this method. This method is being in the process of being standardized at the FNOR and at the ISO. Okay. So what Arcadia and Capella provides, in fact, they have been defined from the operational users to master the complexity, the ever more complex systems that has to be developed, and the more ever more constrained costs. And the idea is to formalize the architecture of the systems, or software or hardware architectures, and provide tools to help them to help the engineers develop them and exploit them. Because once it's formalized, then the tools can exploit this information to improve the design consistency and quality. And because the formalization of the architecture is shared by all the stakeholders and has been defined as such, then the same common engineering reference is used for all the engineering activities, integrating all the disciplines, the engineering disciplines during the architecting activities, and all the co-engineering of all the stakeholders, meaning that there is no more barriers and silos as they usually exist during architecting activities, but every stakeholder can work together on the same reference. And because they work on the same reference, then the architecture can be evaluated earlier in the development life cycle. It provides also means to capitalize engineering know-how of the experts, and to to reuse them. It is collaborative engineering. This means that collaboration between our customers and our co-contractors, subcontractors. It is easy to use, performing, scalable, and all this, in addition to ensure the quality of the architectures that are being defined, provide strong productivity gains. And the maturity is quite high because it is widely deployed in Thales and with success. So before starting the talk, we will see what we will not talk about. We will not talk about Capella features for several reasons. First, because they have been presented last year and demonstrated. And also because you can find it here on the Capella website. You can see the address here. So I will remind just that the fact that Capella provides a methodological browser. This means that you can navigate and edit the architecture along the workflow defined by Arcadia. So you are ensured that you follow the process when using Capella. The semantic browser allows to navigate between elements according to the semantic links between that made them that relate them. The model is a graph, not a tree. It provides means to abstract the information, to zoom in, zoom out in a model, to add information or filter information according to specific concerns, to validate the model according to engineering rules, and when there is a problem in the model, then quick fixes are provided. Semantic delete, when you want to delete an information inside the model, there is an impact analysis stating what will be in danger if you're doing so. Replicable elements, you can reuse fragments of the model in different parts and maintain the coherency between the reference and the replicas. Same for the patterns. You can capitalize in a catalog architectural constructs that you can reuse in a model. HTML generation, transition from system to subsystem. A subpart of the system is identified as a subsystem and can iteratively initialize a new Capella model. All the iterative components becoming the actors of the system, the subsystem. And the multi-viewpoint management that allows to extend the basic Capella with additional concepts, tools that address specific needs for integrating specialty engineering inside Capella, and define and evaluate the architecture according to these different concerns, so as to define the best possible architecture. So what we'll talk about is how the architectures are defined by Capella. By the example, the example that will be used here is the in-flight entertainment system here. You all know about this companion when you take the plane. I will not present exactly what it is because this is the purpose of the first phase of the architecting design according to Arcadia and Capella, and all the models that are developed with Arcadia and Capella define how the system will be implemented. So,
okay. So, just before starting this journey into the architectural design of the IFE, just a reminder, we're not talking about detailed design of software or hardware components. We're talking about architectural design, and the goal of the architectural design is to end up with a preparation for the integration, preparation of the subcontracting. So it's preparing the organization, and it's about evaluating the architecture against different non-functional constraints. To do this, before Capella in Thales, system engineers were mostly using tools like DOORS, Visio, Excel. So we really, this is where we start from. So the first thing, the operational analysis. The operational analysis is about what the users of the system need to accomplish. So we don't we forget about the system boundary and we focus on what are the goals of the users of the system. And to do this, we're going to use operational capabilities, activities, entities, and so on. So in the case of the in-flight entertainment system, we have several entities, which are the crew, the pilot, the cabin crew, the aircraft, the passenger, your personal device, like your iPhone or any phone that you want to connect to the IFE, the ground operator, the airline company, and so on. For example, you could see things like the airline company needs to have some access rights or to manage the digital content of the IFE because in different classes, like business and economy, they don't want to provide the same services and so on. So basically, these entities perform activities, and these activities just exchange information. So what we see here is an operational process. That means it is an highlight among the activities, and this one is about performing an audio announcement. So basically what it says is that the cabin crew is making an audio announcement. So for example, we're going to land or you're going to go through turbulences and so on. The aircraft or something in the aircraft is broadcasting the audio, and at the end the passenger receives and listens to the audio announcement. I don't talk here about what does my system do for this. I can use different means, like operational processes and scenarios, to illustrate the dynamics of this. And for example, here we're using a sequence diagram to materialize the different flying phases. So for example, once you are boarding, you can get some ambience music, and then you get the safety instruction, and then you take off, and then only you can choose a movie, and so on. So basically, this work that we do in the operational analysis is really likely to be shared with the customer, and it helps better understand the system we are developing. So the next step is the system need analysis. And here, we're going to focus on the need and on the boundaries of our system. We identify the actors, and we provide the first description of what the system is supposed to do. But we forget about the solution. We really focus on the need. And for this, we're going to define missions, capabilities, illustrate them with functions, and this is what I'm going to illustrate here. So what we see here, currently building up, is a set of missions and capabilities. So they are basically the same thing as use cases in UML. And it is about what the system is able to do. So my system, one of my missions is to provide cabin management solutions, and this requires to provide audio and video intercommunication means. The mission of my system is to provide entertainment solutions, and the capabilities I am going to do this is providing moving map service, audio entertainment service, video on demand, gaming solutions, and so on. The next step is to perform a first functional analysis of my system. What does it do? So usually we have requirements. The goal here is to illustrate these requirements and describe them more formally than just textual phrases or sentences. So we perform a first high-level functional analysis. What is interesting here is to see that on the top, you cannot really see it, but don't worry, we have the aircraft. The aircraft is actually considered as an actor from the IFE system point of view, because we are interacting with the aircraft. We are receiving notifications and so on. And basically, my system is able to manage the life cycle of services. So according to the energies the aircraft is providing me, I will maybe not activate the same services, so I will have different modes. We'll see that later. The system has to store digital media, to provide means to load digital media and update the movies that the company will provide you in the system. The system has to run different services, so gaming, audio, and so on. And to do this, it relies on some capabilities to perform video or audio streaming. This is what you would see here. And regarding, depending on what you get from the plane, for example, the power and so on, you would determine the different profiles for your system. Once we have these actors and these functions, we can build some sequence diagrams. And for example, this one is interesting because I will come back later on this one. This one is about playing airline-imposed videos. So for example, the safety instructions that are broadcasted on the plane and that you get on the seat in front of you. So what it says is the cabin crew perform the airline-imposed videos. The system is processing these commands and so on, doing some kind of interruption. And then these safety instructions are displayed either on the cabin screen, either on the seat TVs. What is the role of the in-flight entertainment system for audio announcement? We saw in the previous slide that in operational analysis that the cabin crew needs to perform audio announcements. But what is the responsibility and what is the role of the IFE system when it comes to audio announcements? Basically, if the IFE system was in charge of performing this audio announcement, that means it would have higher constraints in terms of safety. It would be more expensive because it would have to be more reliable because audio announcements are critical. So here is what we had in the operational analysis. The cabin crew was making the announcement and magically the aircraft was broadcasting that. Actually, from the system point of view, what happens is we get a notification from the aircraft. The cabin crew actually do the audio announcement using the aircraft hardware, and the IFA systems get a notification from the aircraft. It gets the audio stream, and then the IFA is responsible for displaying interruption messages on your screens and distributing the audio in your headphones. So we see that from the operational analysis and system need analysis, the points of view are really different. And here we really focus on the boundaries. Now, a system has different modes. So for example, it can be fully operational, degraded, halted, it can be in maintenance and so on. And what we have to do at this level of engineering is formalize what functions are supposed to be available in which modes and what triggers the transition between two different modes, for example. So the idea is to relate the transitions between the modes to the data flows that we have already modeled. So the next engineering phase is the logical architecture. The goal of the logical architecture is to provide an intermediate design. We want to manage complexity by hiding the technological constraints, by hiding some implementation details. And the goal of this intermediate solution is to make reuse, product line, capitalization easier. It's easier to do this if your architecture is still at a certain degree of abstraction and not completely stuffed with lots of technical details. So this is basically the goal of the logical architecture. And in comparison with the previous engineering phase, we now focus on the solution. We explain how the system is supposed to work. And for this, we'll first start by establishing clear architecture drivers. What are the main drivers that I'm using to create components? So in the case of the in-flight entertainment system, we have 3 of them. So you cannot read, but I'm going to list them. The first one is just the topology of the plane. You have some things in the front of the plane, you have the seats and so on. So basically we separate what will be the front servers, the cabin terminal, the seat TVs and so on. The second driver is going to be a functional driver. We're trying to group the functions that are correlated. So for example, I have some streaming functions. I'm going to allocate them to the same components. So this would be my second driver in order to reduce the interfaces. And then the third driver is a pattern that we use for some components. We want to isolate what is generic and what is specific to an airline company. When you take a flight and you use the in-flight entertainment system, you don't know whether the system you're using has been made by Thales or by Panasonic, because the airline companies, they override all the user interface. So in this context, we try to isolate what is generic and just isolate what is specific so that we can switch it off, replace it more easily. Once we have our components, this breakdown of components, we need to refine the functional analysis. We need to dive into the detail of the solution without going too deep either. So in this case, this is the manage audio and video diffusions. We have 3 or 4 subfunctions, which are process audio requests, broadcast, display video, and process the audio announcements that come from the plane. And we can see that each of these functions are themselves broken down into sub-functions. So we can zoom in and dive into the detail of these functions and continue the functional analysis. So what you've seen so far are the time lapses, and everything was just fast. And what I'm going to do now is to switch to Capella and do a small demo of what I need to do in the logical architecture based on this refinement of functions and these components that I already have. So I don't know if we said it, but Capella is a tool that is based on Sirius. So we rely intensively on diagrams and so on, and we provide some other tools that you're going to see here. So Daniel talked about this methodological border. Basically, it tells me what I have to do and how to organize my model. And I can display, for example, the play in post video scenario that I showed you previously. I'm plugged. Yeah, okay. So I've talked about this one already. The cabin crew triggers the play of the airline in post video, and it gets to the passenger and so on. So this scenario is that system need analysis. In the logical architecture, I have already done my breakdown of components, and I have also refined my functions and allocated my functions to the components. And the big view is this one. So you don't need to read this, of course, but basically it's just to explain that the mapping or the allocation of the functions to the components have been done already. And what I'm going to do now is a transition from the system need analysis scenario towards the logical architecture, so an automated transition. So we can check here in the logical architecture that on my capability, I don't have a scenario which is called play in post video. This is just to show you that I'm not cheating. And I'm just going to perform a transition, which is an initialization of the scenario at logical architecture given what exists on the system need analysis. So events occur in real time. These are not a time lapse anymore, but still Capella helps you go faster. We don't need this view. I go on the logical architecture. And now on my capability, I have a new scenario which is called play in post video that I'm going to create a diagram for this scenario. Let's call it Capella. It's going to be faster. And this is a result. I'm just going to be a bit smaller. So basically what the tool does, it checks the traceability between the engineering phases and do the mapping to initialize the scenario here. So my work here as an engineer is to complete the scenario because there are some holes and so on. And to do this, so it gives me the contract I have to respect. And to do this, I can create, for example, an architecture diagram. So this is something that Capella provides and helps go faster. On this diagram, I can insert the elements from one scenario, from one mode, or a functional chains, or whatever. So here, I'm selecting the scenarios that I've already done. I have my big diagram that I already had. I'm going to copy the layout of this diagram and paste the layout on this one. So now, here, on this diagram, I can see all the elements that are appearing in my scenario, and I can complete the exchanges between the functions, for example. Or there are also already exist a few of these functional exchanges, so I can synchronize my diagram and get them appear, and then I have a better view of what is available for my scenario. So, okay, the layout would have to be arranged a little bit, but this is basically the idea. Back to the time-lapse and the physical architecture. The physical architecture describes it describes the final solution ready to subcontract, and from which we will perform transitions toward hardware design or software design, or, as we saw this morning, simulation of real-time components and so on. So the first thing at this level is to create the implementation components. So basically the hardware that our system will be based on. And in this case, in the case of the in-flight entertainment system, we made some choices. So the first one is that on the private video display unit, which are the TVs, we have a processor, a bus, we have a dedicated audio processing unit, we have a dedicated MPEG decoder, and the way that we are using to interact with this TV is with a remote control. Another choice has been made for the cabin management unit that the cabin crew is using. On this one, we're going to use a touch screen technology. So it's different from a remote control. They would have, that means that in the case of a remote control, we split the functions. If it's touch screen, the same component will build all of them. And here we just decide that we don't want to have any intelligence in the screen of the cabin. So I'm not going to dive into the detail of what is happening here, but basically it's always the same. We refine the functional analysis, now integrating constraints from the hardware. We, for example, choose which protocol we are using for streaming and so on. We define a data model that will formalize the exchanges between the functions, and we relate all this, and we refine the functional chains, refine the scenarios, and we continue. For example, here, the idea is that we have functional exchanges between functions, of course, that are allocated to component exchanges, so exchanges, interfaces, communication between components. So here it would be the streaming protocol. And the streaming protocol is still at some kind of application level. And this would be carried by what we call a physical path, which is, for example, the network, which would go around next to a set of switches. So all of this is consistent. So Capella helps building consistent views about this. And the main criteria here in the physical architecture is just to be sure we are at the right level of granularity, that we don't do the job of the people like software developers, for example, and the physical architecture has to be used as a co-engineering place so that we agree on the contract. So at the end, this is what an in-flight entertainment system looks like. So you have the TV displays, you have some modules, you have the aircraft interface, and this is some specifically designed hardware because there are lots of constraints in terms of mass, cost, bandwidth, and so on. And Daniel, I think it's now for you.
Okay, just a few additional words. to say that we see Capella as a backbone of the engineering activities because, as we said at the beginning, it is the common reference for all the stakeholders during the engineering activities for architectural design, but also for system engineering as a whole. So we may, in fact, integrate Capella with a lot of different activities, architecting with a lot of different activities, and Capella with a lot of different tools for implementing the global workflow of the system engineering. And we can see that this is the vision, a vision of a possible tool that could be integrated with Capella. It seems a lot, but in fact it's a reachable vision because it has been implemented inside Thales for all the different projects we have, all of them in different combinations, except maybe for simulation, but we are working on it. But we can see outside this capitalize the know-how of our experts, so it's inside our engineering environment, but everybody should have its own ultimately. But outside Thales, in fact, we can see that in Polarsis there are already some tools that are available for certain engineering activities, integrated engineering activities. And to reach this kind of support outside Thales, in fact, we are in the process of building an open innovation scheme with actors on the whole value chain of the engineering environments. So it is well the industry, the end users of Capella and the workbenches, the research and academia that will enrich and provide the courses, training courses for the engineers that will come to the whole here community. The tool and techno providers that will provide additional solutions to Capella, and service provider that will help the usage of the solutions for the end user. So all this and the community, of course, for sharing the results. So all these stakeholders, in fact, works in synergy because, for example, when a young engineer has been trained to Capella, and then is available for developing additional solution that will be used by the end user and will be added to the shared resources inside the communities and standardized. So in fact, at this stage, we are building this through the usage of collaborative projects, French collaborative projects and European collaborative projects. And Clarity, a specific collaborative project, is specifically dedicated to the open sourcing and the ecosystem building around Capella, in addition to the further innovation of the solution. And the ecosystem is building up and is spreading, in fact, because when you see all these actors here that are in the open innovation scheme around Capella, they are involved in collaborative projects, but some of them are not outside, but they take the benefit of the critical mass that is being built around Capella to join and to benefit from this ecosystem. So you're welcome to join if you're interested, and we can. You can find here all the resources that you can have. The DFE model is also available on the Capella website.
So it's available for download, and there's about 80 slides that explain the methodology and gives tips and tricks about the model.
Yeah, questions?
Going back to some of the views at the beginning, where you had the aircraft as an actor, don't you also need some views of the in-flight entertainment system as a subsystem kind of the aircraft system? I mean, where do you kind of bring in all the other connections
Yeah.
with the rest of the aircraft?
It could come from architecture frameworks like DODAF, MODAF, or things like this. It's something that would be before Capella and from which we would do a transition.
So it's not far that out, because NASA kind of has an all view that shows your system
Yeah.
as how it relates to the rest of the larger system kind of thing, like a component of the space communication network.
So if we really wanted to see the different interfaces with the aircraft, we would probably split the aircraft actor, because this one is a dummy model, it's a sample model. But we would probably split the actor aircraft in several boxes, and we would have different interactions or interfaces with each of these boxes. It's just here we were really like with high granularity. This is the aircraft. Basically, I could
I mean, in this
break down in.
context, it makes sense
Yeah.
in a way,
Yeah.
but I just didn't kind of envision it.
Yeah, in real life.
The only place
Yeah.
the aircraft would appear.
Yeah, yeah. And from a learning point of view or pedagogical point of view, this is interesting to see that something you are inside is actually an actor of yourself. And it's just, it's like the difference between the audio announcements, between operational analysis and system analysis. It's, from the pedagogical point of view, it is interesting.
Well, I wish this had existed back when I was doing a lot of IB&B. It would have been helpful.
Yeah. We have some projects who have established really nice frameworks for the IV&V, and they use the capabilities, functional chains as the main driver of the validation campaigns and so on. And, yeah. We probably have some examples in the papers we have on the website. There are some use cases, and we have described this.
So these slides are available on Capella's site or somewhere?
These ones exactly no, but they will probably be at some point, but the equivalent of this and much more is available on the website. Yeah.
And I guess those slides will be available on the Eclipse website.
Yeah.
No way.
It's just about 40 megas, because there's lots of videos. But, yeah.
Put them on Dropbox and
Yeah. Okay.
okay, thank you very much.
Thank you.